Alright, so this is the third video in our exploration of Lagrange's theorem. So exploration of Lagrange's theorem. Right. And so this is our third part in this video episode, video series, obsessed with episodes. So what's the main idea here? We're saying, look, Lagrange's theorem talks about this idea. Suppose we have G, right? So G is some finite group. G is finite. We have H, and we're saying H is a subgroup of G. Now, what's the relationship between the cardinality of H, or the order of H, and the order of G? In particular, does the order of H divide the order of G? That's the question. Is this true? Well, we're not sure yet, and that's why we're calling it an exploration. We're trying to figure out if this is true or not. Well, one thing we realize is, one thing we've been working on is, the strategy has been, well, if we want to figure out whether whether the order of H divides the order of G, perhaps, I mean, it's really hard to find a relationship between the cardinality of H and the cardinality of G, or the order of G. It's really hard to find a relationship, right? These things seem to be so arbitrary. This G could be any group, H could be any subgroup. How can we find out a relationship between the cardinality of H and the cardinality of G, or the order of H and the order of G, right? That seems to be the key problem here. But so the tactic we've been using is, maybe we can study it through this idea of cosets. So we get a group G, right? So we have some group G over here. Okay, fine. We have a subgroup H of it, right? Then if we pick some little element G of G, maybe we can study this thing here, GH, which we're going to call the left corset of H, right? Right, the left corset of H, right? So that means we get every element of H and left multiplied by G. And the idea was that we saw in previous videos that it turns out that the order of GH actually equals to the order of H. Perhaps we may not be able to figure out what's the relation between the order of H and the order of G, but if we can find a relationship between the order of GH and the order of G, well, then we've also actually implicitly found a relation between the order of H and the order of G, because the order of GH again equals to the order of H. So that's kind of the indirect route. We've learned a lot of things about these corsets, right? These left corsets in this case. We've learned a lot of things about them. And last time we were saying, maybe we can even extend this strategy a little more. So the idea is, okay, fine. Usually when we do arithmetic, right? So because what we're really wondering is, okay, fine, maybe we don't know whether order of H divides order of G. But what about the order of GH? Does the order of the left corset divide the order of the group? Right. Notice if we can prove this, we've also implicitly proved that the order of H divides the order of G, right? Because the order of GH, the corset, is the same as the order of GH. Okay, so what would it mean for the order of GH, the left corset, to divide the order of the group? Well, what that would mean is, we just have to think of usual arithmetic. For instance, what does it mean to say that 2 divides 6? When we say 2 divides 6, what are we really saying? We're saying, look, if we have, let's say, 6 blocks, 1, 2, 3, how many are those? 1, 2, 3, 4, 5. Okay, let's add a 6th block right here. Okay, if we have 6 blocks, well, if we say that 2 divides 3, we're saying that we could get the 6 blocks and split them up into 3 blocks of 3. That is, we could split them up into this block here of 3, this collection of 3 blocks, and then this collection of 3 blocks. And if you put those two collections of 3 blocks together, we end up with 6. That is, what we're saying is 6 blocks can be partitioned into 2 blocks of 3. Right? That's the idea. So with that intuition, well, if we say that the order of GH if let's say we're trying to see if the order of GH divides the order of G, well, maybe we're also trying to think about this idea. Well, suppose we got the group G right here. Suppose we got the group G right here. Okay? Could we perhaps break it up just like we broke up the blocks here? Right? Could we perhaps break G up into a bunch of cosets? Maybe we'll call this coset G1H, G2H, G3H, and maybe G4H. Could we possibly break up G into these four cosets is the idea. Okay, let's get some water. Just a second, actually, can't open the window. Okay, so, right, this is the idea. Because if we can get the group G and break it up into these cosets like this, then it would mean that, remember, each of these cosets has the size cardinality of H. So with this we may be able to conclude that cardinality of GH divides the cardinality of G, and thus the cardinality of H divides the cardinality of G. But this partition here is, does it even make sense? So as before we're exploring, we're thinking about, well, okay, can we study these cosets more carefully? And so let's continue from there. And the idea we started with was, okay, we've been working too abstractly, let's be more specific. Consider the group G equals to Z. And let's consider the group H equals to 4Z, right? So we're considering the set of integers under addition. That's a group. Please verify that if there's confusion. And then 4Z is also a group, right? And since 4Z is a subset of Z and 4Z is a group, it's the case that 4Z is a subgroup of Z, right? Under the same, of course, group operation. So now we've gotten ourselves this scenario. We've gotten ourselves a group. Okay, let's do here. We've gotten ourselves a group G. In this case, it's Z. We've picked a subgroup of Z, which we are calling 4Z. And what in particular we want to talk about is the cosets, the left cosets of, usually, remember before, analogously we'd said, look, if we have a group G right here, if we have a group G, okay, if we have a group G and we take a subgroup of the group G, let's call the subgroup H, then by picking elements of G we can form cosets, right? And we said the cosets are GH, which would just be, well, if the group G is being considered under this operation of dot, then GH would just take every element of H and left multiplied by G, right? GH2 blah blah blah, right? GHK, alright? So natural question we think about is, analogously, now we have Z here, our G is Z, and 4Z is our H. What will the cosets look like? Now we're looking at things under addition. So what that means is we'll have to pick some element of the group, in this case our set of integers. We could pick, for instance, 0, right? Well, 0 plus, okay, this was written badly, but 0 plus 4Z, right, would be how we'd write this coset. Maybe let's write it better just to be completely clear. So consider, for instance, 0 plus 4Z, right? That would be the equivalent of our left coset, because here we got G multiplied by H because our operation was dot, but over here operation is plus. So it's going to be 0, any element of the group of integers, plus 4Z, right? And what is this? Well, this is the set of all, in this case 0 plus 4Z would just give us 0. So really this is the set of all 4I such that I is an integer. Right? That seems pretty clear. That's what 0 plus 4Z will give us. What about the other cosets? Let's think of some more cosets. Well, what's 1 plus 4Z going to give us? 1 plus 4Z is just going to give us, well, all elements of the form 1 plus 4I such that I is an integer. That's pretty clear, isn't it? Right? Because every element is of the form 1 plus I mean, one of the elements in this would be 1 plus 4 times 1, 1 plus 4 times 2, 1 plus 4 times 3, 1 plus 4 times 4, which is 1 plus 4 times any integer. Right? The set of all 1 plus 4i such that I is an element of z is 1 plus 4z. Right? What's 2 plus 4z going to be? 2 plus 4z, right, is going to be exactly what we think it is. All elements of the form 2 plus 4i such that I is an integer. Alright, let's write a couple more because this will give us some really nice we'll probably be able to derive some nice insights from this. 3 plus 4z now becomes what's that? 3 plus 4i, all 3 plus 4i such that I is an integer. Okay, what's 4 plus 4z gonna give us? Right, let's do a couple more. 4 plus 4z is gonna give us 4 plus 4i such that I is an integer. Okay, what about 5 plus 4z? 5 plus 4z is going to give us all 5 plus 4i such that I is an integer. Okay, 6 plus 6z, where do you want to go? Actually, yeah, let's stop at 6. 6 seems perfect. 6 plus 6z is going to give us all 6 plus 4i such that I is an integer. Okay, so that's where we're at now. So these are just some of the corsets, right? Now it seems that there are, how many corsets are there is the question. How many corsets are there really of 4z in z? How many left corsets are there of 4z in z is the question. Well, so far we've started with 0, 1, 2, 3, 4. I mean, it appears that this process can go on forever. But then the question becomes, does it really go on forever? And let's check that. So for instance, 0 plus 4z contains all elements of the form, right? We said 0 plus 4z contains all elements of the form 4i such that I is an integer, right? That's what 4z was. 0 plus 4z we said was this: the set of all 4i such that I is an element of the integers, was the idea. Well, what's another way of stating this? If we're looking at the set of all I such that all integers I such that 4i is okay, just if we're looking at all, okay, the set 0 plus 4z could also be thought of as all integers that are divisible by 4. Does that make sense? Right? Because, well, all elements of the form 4i, right? All elements of the form 4i, which means all of them are divisible by 4. And could there be some integer that's not divisible by 4? Could there be an integer that's divisible by 4 that's not in this corset 0 plus 4z? Well, I mean, basic thought says no, right? Because every integer that's divisible by 4 is of the form 4i, where I is some integer, right? So indeed 0 plus 4z refers to all elements that are divisible by 4. So now the question becomes, if we look at 0 plus 4z and 1 plus 4z, right? 1 plus 4z was different, wasn't it? It was, okay, let's write that well. We're getting too excited here. So maybe let's erase all of this. Try to be neat for once. So what about 1 plus 4z? Well, 1 plus 4z is just all elements, as we saw, of the form 1 plus 4i such that I is an integer. Okay, well, what's another way of stating the elements of 1 plus 4z? We could refer to it as 1 plus 4i such that I is in z. Another way we could do it is using divisibility. Can you see how to do that? Well, the idea is 1 plus 4z could be thought of as the set of all elements such that when you divide them by 4 you get a remainder of 1. Because think about it, any element of the form 1 plus 4i, when we divide it by 4, the remainder, right, the remainder is 1, right? Because 4 is going to divide this part, but 4 is not going to divide 1. So, question, does 0 plus 4z and 1 plus 4z, can they have any elements in common? Right? If all elements of 0 plus 4z are elements that are divisible by 4, and all elements of 1 plus 4z are elements that when you divide by 4 you get a remainder of 1, can 1 plus 4z and 0 plus 4z ever have an element in common? right? And the realization here is, of course not, right? So 0 plus 4z does not equal at all. They have no elements in common, in fact, right? So they're not equal, and in fact they have no elements in common. This is not true. So far, here's what we can say. Well, if we looked at the set of integers, right? So if we look at the set of integers, we're able to make a few conclusions so far. So, okay, let's go back up here. All right. If we look at the set of integers, right? How do we write this better? So, okay, hard eraser, right there. Okay. All right, there goes the artist. All right, let's draw this wall. All right, so let's draw it like that. So the set of integers z, right, could be thought of as 0, 1, minus 1, 2, minus 2, 3, minus 3. Actually, we wanted to focus more. Okay, no problem. 4, minus 4, 5, minus 5, 6, let's go till 8, minus 6. Okay, let's erase this stuff. Hard eraser, blah blah blah. Okay, done this already. So 6 minus 6, minus 7, minus 8. Let's stop at minus 8, and then 7, and let's go till 8. Okay, so there we are. All of it doesn't fit, but actually it can be made to fit. So notice, we said that 0 plus 4z were all elements which are divisible by 4, right? So for instance, let's see, maybe we can get some color as well. So colors might be helpful here. Let's say we pick red, okay? So, oh shit, okay, the colors actually are not working, are they? Actually they do, right? So this is an element that is divisible by 4, so it's an element of 0 plus 4z, right? So we're going to say purple. Let this purple color stand for elements of 0 plus 4z, and let this let this dark color stand for elements of 1 plus 4z. All right, so if we look at 0 plus 4z, well, 0 plus 4z we said was a set of all elements which are divisible by 4. So 0 is divisible by 4, 4 is divisible by 4, 8 is divisible by 4, negative 4 is divisible by 4, negative 8 is divisible by 4. All these elements here are divisible by 4. Okay, and of course, how many elements are there for 0 plus 4z? Or another way of stating it is, how many elements are there such that, how many integers exist such that they are divisible by 4? The answer turns out to be infinitely many. So there are infinitely many elements of 0 plus 4z. Okay, that's clear. Now if we look at 1 plus 4z, how about 1 plus 4z? Well, we said that 1 plus 4z and 0 plus 4z cannot have elements in common, because 0 plus 4z is talking about, well, all elements which when you divide by 4 you get a remainder of 0. 1 plus 4z is saying all elements which when you divide by 4 you get a remainder of 1. Right? So they can't be the same. You can't have both a remainder of 0 and a remainder of 1. Okay. So now let's work with let's think about 1 plus 4z. What are the elements? Well, if we divide 1 by 4, well, what do we get? Well, we get a remainder of 1, right? If we divide 5 by 4, we get a remainder of 1. If we divide which other numbers are going to work here? Well, actually negative 3 as well, right, would give us a remainder of 1. Every fourth one. 1, right, 1, 2, 3, 4. Actually every fifth one. So 1, 2, 3, 4. Yeah. If we divide negative 3 by 4, we also get a remainder of 1. Right? That seems accurate, isn't it? Negative 3. Oh no, actually, yeah, that may not be. If you're considering things mod 4, then yeah, maybe not, maybe not. Negative 3 is congruent to 3 mod 4. So yeah, negative 3 is not in the list. Okay, that's not true. Alright. We're looking for all things when divided by 4 give a remainder of 1. Okay. Alright. So is there anything else? Well, certain things would work. For instance, oh, wait a second. No, negative 3 does work. What are we saying? Negative 3 is congruent. Sure about that. Negative 3 is congruent to 1 mod 4. Okay. Right. Kind of makes sense. Negative 1 would be 3. Negative 2 would be 2. Negative 3 would be 1. Yeah, okay. So actually negative 3 would work right here. So I guess it's up to you to try to convince yourself that this is true. Right? So, and in fact, it seems to be a pattern. Every fifth thing from, let's say, 1, 2, 3, 4. Every fourth thing, let's say, gives a remainder of 1 when divided by 5. So the next one is going to be, well, 9 is going to give a remainder of 1 when divided by, let's say, 9 over here. 9 is going to give a remainder of 1 when divided by 4. From here, we'd have something like, well, every fourth one, 1, 2, 3, 4. So negative 7, for instance, right? When divided by 3 gives us negative 3, which is 1. So there you go. So basically, we said before that the purple things, elements of 0 plus 4z and elements of 1 plus 4z have nothing in common. These two sets are not equal to each other. But in particular, we see that 0 plus 4z and 1 plus 4z are covering different elements of the number line of integers, right? So let's see if we can fill in some more things in this number line. So we're going to pick a different color just for fun. Let's pick green. Okay, why not? Let's pick green. Oh, well, green doesn't. Oh, wait, we got green, people. All right. So we have green, we have green. Okay, now we have green. So let's say let's green stand for the next coset, 2 plus 4z. What's 2 plus 4z? Well, that's the set of all elements, all integers, which when divided by 4 give us a remainder of 2. That's pretty clear, isn't it? If we have something of the form 1 plus 4i, sorry, 2 plus 4i, if we divide it by 4, the end result is, well, we could think of it as the 4 is going to divide out the 4i and we'll be left with 2. Okay, so that's one way to think about it. If we want just a concrete example, is a number, what's an element in 2 plus 4 is something like 6. What's 6 divided by 4? This is just a demonstration, not a proof, but right, the remainder is 2. And all elements of the form 2 plus 4i give a remainder of 2. Please check that if it's confusing to you. Okay, so let's now try to fill in our number line again. What integers are there such that when you divide them by 4 you get a remainder of 2? Well, 1 is just 2, right? If we divide 2 by 4 we get a remainder of 2. Okay, what else is going to give us a remainder of 2 when divided by 4? Well, I mean, another one is going to be negative 2, right? Again, it's up to you to check that this is true, right? Negative 2 turns out to be congruent to 2 mod 4, so yes, indeed. The next thing that's going to be divisible by 4, right, is the next thing that's going to give us a remainder of 2 when divided by 4 is going to be, what, the fourth thing, right? 6. 6 divided by 4 gives us a remainder of 2. Right, so that was every fourth thing. So from here I would say every fourth thing as well. So right here, negative 6 will also give us a remainder of 2 when divided by 4, etc., etc. So, right, and again, notice something interesting. Can any element of the coset 2 plus 4z also be an element of 1 plus 4z? Well, we notice that, can that happen? Now, please take a few seconds to think about that. Well, we already noticed that 0 plus 4z and 1 plus 4z will have nothing in common. Why? The reason was when you divide any element of the coset 0 plus 4z by 4, you get a remainder of 0. When you divide the element of 1 plus 4z by 4, you get a remainder of 1. And since numbers that have a remainder of 0 can't also have remainders of 1, 0 plus 4z and 1 plus 4z were said to be disjoint. They have no elements in common. What about 2 plus 4z? Can 2 plus 4z have an element? Does 2 plus 4z have an element in common with 0 plus 4z? Well, 2 plus 4z is the set of all elements which leave a remainder of 2 when divided by 4. And 0 plus 4z is the set of all elements which leave a remainder of 0 when divided by 2. So how can a number have a remainder of 0 and a remainder of 2 when divided by 4? Right? That doesn't make any sense. So please verify that. In fact, please try and check if any of these three, any pair of these cosets, 0 plus 4z, 1 plus 4z, and 2 plus 4z, if any pair of these could have any elements in common. And when you check, you'll realize that indeed no. All these cosets are disjoint. Okay. So they are filling in different parts of the number line. Okay. So what's our next thing? Let's pick another color. Let's see. We haven't tried red, you know. Oh yeah. Some of us are colorblind though. So whatever this color is it red? Who knows? Okay. So the next candidate is 3 plus 4z. Okay. Well, is 3 plus 4z, what does 3 plus 4z stand for? Right. Again, it's, well, the set of all elements of the form 3 plus 4i such that I is an integer, sure. But it can also be thought of as the set of all elements which when divided by 4 give us a remainder of 3. Right. That's one way to think about it. So, which elements are there in our number line which when you divide them by 4, you get a remainder of 3? Well, one of them is just 3, right? 3 divided by 4 gives us a remainder of 3. Okay, what about 7? Well, 7 divided by 4 also gives us a remainder of 3. And by the same token, well, let's see, negative 1 divided by 4. What does that give us a remainder of? Oh, that does give us a remainder of 3, actually. Yes, that's right. Every fourth one from the brown. Every fourth one. And how about negative 5? Well, negative 5 divided by 4, right? Negative 5 divided by 4, what's that going to give us? Well, it's going to give us a remainder of negative 1. But negative 1 is really 3. So, again, it's up to you to verify that this is true. Right? So, now we have negative 5. So, first of all, notice, at least if we consider our number line from, let's say, actually negative 9 too, let's say now from negative 8. From negative 8 to 9, we see that these 4 cosets, right, so let's go back to black, right, we see that these 4 cosets, right here, 0 plus 4z, 1 plus 4z, 2 plus 4z, 3 plus 4z, were enough to fill up our entire number line from, let's say, negative 9 to 9, right? And actually, if we think deeper, we'll realize that it's actually enough to fill up or maybe that's the question, are these cosets enough to fill up the entire number line? Well, okay, maybe let's check a few facts. For instance, how about the coset 4 plus 4z? We never considered that. What is 4 plus 4z? 4 plus 4z is the set of all elements which when divided by 4 will give us a remainder of what? Right, so let's think about it this way, right? So 4 plus 4z is the set of all 4 plus 4i such that I is an integer, right? That's what we said. Well, think about any element of the form 4 plus 4i. If we divide such an element by 4, what do we get? Well, we get a remainder of 0, right? Which means that all elements of 4 plus 4z leave a remainder of 0 when divided by 4. But, remember we said that 0 plus 4z, the coset 0 plus 4z, is the set of all elements which when divided by 4 give a remainder of 0. What this tells us is that if an element is in 4 plus 4z, it's also an element of 0 plus 4z, right? Kind of clear? Every element in the coset 4 plus 4z gives a remainder of 0 when divided by 4. But all such elements are contained in 0 plus 4z, because 0 plus 4z is the set of all integers which when divided by 4 give a remainder of 0. Okay, so now we have that 4 plus 4z is a subset of 0 plus 4z. How about 0 plus 4z? if an element is such that, so we're trying to check this, is 0 plus 4z a subset of 4 plus 4z? Right? Because if we check these two things, then we might be able to conclude that 4 plus 4z equals to 0 plus 4z. In which case, if we can conclude this, then it means that the coset 4 plus 4z is unnecessary. 0 plus 4z already, the elements of z that are in 0 plus 4z are also the elements in 4 plus 4z. So the 4 plus 4z coset is kind of redundant, unnecessary. Right? And it kind of makes sense on our picture here. Right? So all elements of the form 4 plus 4z, what are some of those elements? For instance, 4 plus 4 times 0 would be an element of 4 plus 4z, which would be 4. 4 is already covered by the coset 0 plus 4z. That was purple, remember? What about 4 plus 4 times 1? That's also an element of 4 plus 4z. Well, that just turns out to be 8. 8 was already covered by the purple. What about 4 plus 4 times negative 1? Well, that just turns out to be 0. 0 was also covered by the purple. What about 4 plus 4 times negative 2? Well, that's just negative 8 plus 4, negative 4. Negative 4 was also covered by the purple. So, at least visually, we notice that 0 plus 4z, the coset 0 plus 4z, covers everything that the coset 4 plus 4z covers. So that means that at least 4 plus 4z is a subset of 0 plus 4z. Now the question becomes, just because every element of 4 plus 4z is in 0 plus 4z, doesn't necessarily mean that every element of 0 plus 4z is also in 4 plus 4z. So it's worth checking, right? So this feels like a mouthful, but here's what we're saying. So far we know that this is true. 4 plus 4z, the coset 4 plus 4z is a subset of the coset 0 plus 4z. We know that. That is true. Because, once again, every element, every integer which is divisible by 4 is in 4z. So, since every element of the form 4 plus 4z also is divisible by 4, gives a remainder of 0 when divided by 4, then every element in here must also be in 0 plus 4z. But is it true that 0 plus 4z is also a subset of 4 plus 4z? That's what we need to check. Is this true? Well, let's see. This is the question mark here. Right? Is that a true statement? Well, what would it mean to say that? So, to prove that this coset is a subset of this coset, all we need to do is show that, well, if we pick any element of 4z, if we pick any element over here, it's also in 4 plus 4z. So for instance, let 4i be an element of 0 plus 4z. Right? That's one way to look at it. So now the question is, we need to prove that 4i is also an element of 4 plus 4z. Okay. Well, how do we actually prove this? It's a good question. So let's try and think about that. It doesn't seem to be I mean, there is another roundabout way to do this, but I don't know if do we want to go that route or not. Okay. See if there's an obvious way to do this. We want to write 4i. The question becomes, how do you write 4i? How can we make 4i equal to 4 plus 4 times some j? Okay, does such a j exist is the question. Well, actually, it turns out that it does, doesn't it? Because, okay, let's see. Now we have that 4i minus 4 equals to 4j, which means that j equals to I minus 1. Oh, that's right. Okay, so it turns out that if we have some 4i element of 0 plus 4z, right? If we consider the element 4 plus 4 times I minus 1, what do we notice? Well, this is the same as 4 plus 4i minus 4, which gives us 4i. Right? But remember, if I is an integer, I minus 1 is also an integer. So this element 4 plus 4 plus 4I minus 1 is an element of the coset 4 plus 4z. Right? But it's also equal to 4i. So we've just shown that if you take any element 4i in 0 plus 4z, that element 4i is also an element of 4 plus 4z. So that's enough to conclude that indeed 0 plus 4z is actually a subset of 4 plus 4z. Right? That's something we can now conclude. But we already proved before that 4 plus 4z is also a subset of 0 plus 4z. So now we can draw the following conclusion. If 0 plus 4z is a subset of 4 plus 4z, and 4 plus 4z is a subset of 0 plus 4z, what does that mean? Well, we know that that means that the coset 0 plus 4z must equal to the coset 4 plus 4z. Right. Which kind of agrees with our intuition, what we observed before here. We observed that, look, 0 plus 4z was in purple, right? And we noticed that every element of 4 plus 4z, namely 4 is an element of 4 plus 4z, it's equivalent to 4 plus 40, and whatever that element was, it was also covered by 0 plus 4z. This element is also an element of 4 plus 4z, right? It's the element 4 plus 4 times negative 1, which is 0. This is an element of 4 plus 4z, but it's also an element of 0 plus 4z. And we've just proved that 0 plus 4z is the same as 4 plus 4z. What this means is that if we're going to look at, we don't need to look at the coset 4 plus 4z. 0 plus 4z is enough. It covers all elements of 4 plus 4z. Right? What about, let's see, what about the coset 6 plus 4z? Okay, actually, let's think about 5 plus 4z. We just looked at 4 plus 4z. We just concluded the following, that 4 plus 4z is equal to 0 plus 4z. We just concluded that. Okay. What about 5 plus 4z? What are the elements of 5 plus 4z? Some of the elements we have here are, well, 5 plus 4 times 0 would be 5. 5 would be an element of 5 plus 4z. Well, 5 is covered by black. What was black? 1 plus 4z. What's another element of 5 plus 4z that's in our list here? Maybe if we set z equals to negative 1, then we have 5 plus 4 times minus 1, which is the same as 1. Well, 1 is an element of 5 plus 4z, right? But 1 is also an element of black, which is 1 plus 4z, right? So this leads us to ask the question, is it true that 5 plus 4z is actually equal to 1 plus 4z? Right? Is that true? And I mean, what about 6 plus 4z? Is 6 plus 4z then equal to 2 plus 4z? What about 7 plus 4z? Is 7 plus 4z equals to 3 plus 4z? Right? What about 8? What's 8 plus 4z going to equal to? Right? Is that equal to 0 plus 4z? It seems like we're circling around, aren't we? So 4 plus 4z is a set of all. So this is actually, this is something we leave you to check, and there's some intuition to it too, right? Like, what are the elements of 1 plus 4z? Those are the elements which, when divided by 4, give a remainder of 1. What are the elements of 5 plus 4z? Well, all elements of 5 plus 4z have the following property. They are of the form 5 plus 4i. If we divide 5 plus 4i by 4, well, we divide by 4, and this part is going to give us 0. We'd end up with 5 over 4 plus I. Right? So, and then over here, the remainder when divide 5 by 4 would be 1. So it's kind of intuitive that 5 plus 4z when divided by 4 gives us a remainder of 1. So, but it's really up to you to check. In fact, here's the claim that we're making, and this is something for you to check. Just make sure you really understand what we're saying. We're saying that, look, if we consider the entire number line, here we only considered from negative 9 to 9, but if we consider the entire number line, these 4 cosets, 0 plus 4z, 1 plus 4z, 2 plus 4z, and 3 plus 4z, are enough to cover the entire number line, and in fact they are also disjoint. What does this mean? Right, so this is really, if you're still not convinced, then this is something to really verify and make sure it's understood. So here's the idea. If we looked, please convince yourself that this is true. If we looked at the set Z, the set of integers, we can partition the set of integers as follows. We can partition the set of integers into 4 cosets. All elements of all integers of the coset 0 plus 4z. I was wondering when the pen will misbehave. Okay, it's now misbehaving. Alright, let's first erase this stuff. So now we have 0 plus 4z, right? So if we got all the elements of 0 plus 4z and put them in this box, and got all elements of 1 plus 4z and put them in this box, and got elements of 2 plus 4z and put them in this box, and got elements of 3 plus 4z and put them in this box, would have actually covered the entire set of integers. That is, the set of integers can be partitioned to elements of integers that belong to this coset, elements of integers that belong to this coset, and this coset. So please do check that the coset 0 plus 4z, 1 plus 4z, 2 plus 4z, 3 plus 4z are enough to partition the set of integers, right? So we've now seen an example of where this partitioning actually makes sense, of where we get a group and we break it up into cosets, right? And this is pretty interesting. So, but still, I mean, Z is kind of, what's the cardinality of Z? Well, we're making some progress, but the cardinality of Z is what? How many integers are there? Okay, infinitely many, right? So it's not really, infinity is not a number, but we're just trying to say that there are infinitely many integers. Okay, well, and how many cosets have we found to cover all the integers? Just 4. So, I mean, would have wanted to say that if we took any coset, let's say 2 plus 4z, right? So here's kind of what would have wanted to conclude, that if we took any coset, like let's say 2 plus 4z, and we'll consider its size, and then divided that by z, would kind of want to get a number. But the problem is that the cardinality of z is infinite, and 2 plus 4z contains all elements which, when divided by 4, give a remainder of 2. There are infinitely many such elements. So not quite, but we have learned something important. We've learned that we can actually partition the set of integers into these cosets. So these left cosets that we came up with are not completely nonsense. They enable us to partition sets. Perhaps, now this is the leap, perhaps if we got a group that's actually finite, took some subset H of that group, maybe we'll also be able to do the same thing. We'll be able to get the group, our group G, partition it, write it like G1H, G2H, G3H, and maybe 3 partitions, and then from here be able to conclude that, right, because since each of the G1H's have the same cardinality, we'd be able to conclude that maybe the cardinality of G1H equals to the cardinality of, the cardinality of G1H divides the cardinality of G, which would enable us to conclude the cardinality of H must divide the cardinality of G. Right, so what the example we've done here tells us that maybe there is hope. There is hope that we can actually successfully partition some group into a bunch of cosets, and on hopefully finitely many cosets. Okay, So, but then the question becomes, can we actually partition a group into finitely many cosets? We still haven't proved this. And so that's the first question, right? Is, can we partition? Okay. Pen's really misbehaving. But can we break up a group G into these cosets? And if we can break it up, how? How can we prove that? How can we prove that? How can we prove? Okay, writing is messing with things. So how can we prove that every finite group G can be broken up into cosets of the form GH, and that actually all these cosets are going to partition the entire group, right? That is the key question. Okay, we've actually run out of time, so this is a good place to stop. Please do think about how would we prove that a group can be partitioned into cosets, right? So that's the first thing, right? Remember, our integer example was really beautiful, because here's what he was saying. Look, okay, we get the set of integers, we get the group of integers right here, okay? We create 4 cosets, okay? Let's write it out again, right? Here we're considering our subgroup to be 4z. We look at the coset 0 plus 4z. We looked at the coset 1 plus 4z. We looked at the coset 2 plus 4z. And we looked at the coset 3 plus 4z. The conclusion we came to was actually each of these cosets is disjoint. Okay? That is, no element of 0 plus 4z in 0, 1 is, let's say, in 0 plus 1 is in 1 plus 4z. The cosets are disjoint. That is, the elements of the integers that are here cannot be found here or here or here. And every integer falls into one of these cosets. What does that tell us? Well, these cosets partition the entire set of integers, right? So, does that ring a bell? You have a collection of objects, G or X. These elements, we create some sort of classes. In this case, there are cosets. Some classes may be alpha, beta, and gamma. Every X belongs to one of these alphas, and no X can go into 2 different alphas. What does that remind you of? Alright, that's what we'll be pursuing in the next in our next video in exploration of Lagrange's theorem. But I guess just as a reminder, here's our goal. Our goal is to prove this. If G is a finite group, if G is finite, and we take some subgroup H of this group G, is it true that the order of H must divide the order of G? That's the question. And thank you very much for joining us in this exploration. And yeah, we'll continue with it in future videos. Otherwise, have a relentless week, and bye.